Why does salt form crystals? Why does water stay liquid? Why are diamonds so hard? The answer to all of these questions lies in one thing: chemical bonding. Chemical bonding is the reason atoms stick together to form everything around us: water, salt, metals, even your DNA. More formally, a chemical bond is a stable attraction between atoms that results in a lower energy, more stable arrangement. Atoms bond because it makes them more stable, like people forming teams to get things done more easily. Let's start with energy. Imagine two magnets. When you bring them close, they snap together. That's like atoms forming a bond. When they do, the system loses energy, and that's good. Lower energy means more stability. If you plot energy versus distance between atoms, you get a curve. Far apart, there's no interaction. As they get closer, attraction dominates and energy drops. But if they get too close, repulsion kicks in and energy shoots up. The sweet spot, the lowest point on the curve, is the bond length. That's where the atoms settle. So bonds form when atoms can lower their total energy by coming together. Now, what makes bonding possible? Electrons and forces. Atoms have a positively charged nucleus and negatively charged electrons. Electrons live in orbitals, regions where they're likely to be found. Two key forces are at play: attraction between nuclei and electrons, and repulsion between like charges. But electrons aren't just particles. They behave like waves. They can spread out and overlap. That overlap is what allows electrons to be shared or transferred between atoms. That's bonding. There are three main types of strong chemical bonds: covalent, ionic, and metallic. Let's start with covalent. In a covalent bond, atoms share electrons. Take hydrogen gas, H2. Each hydrogen atom has one electron. When they share, they form a pair. Now each feels like it has two electrons, like helium. That shared pair is a covalent bond. We can draw it as H-H. Oxygen gas, O2, shares two pairs, so it has a double bond. Nitrogen gas, N2, shares three pairs, a triple bond. More shared pairs means stronger, shorter bonds. But not all sharing is equal. Electronegativity is a measure of how strongly an atom pulls electrons. If two atoms have similar electronegativity, the bond is nonpolar, equal sharing. If one pulls harder, the bond is polar, unequal sharing. Water is a classic example. Oxygen pulls electrons more than hydrogen, so the OH bonds are polar. Oxygen gets a partial negative charge, hydrogen gets a partial positive. That makes water a polar molecule, and that polarity explains a lot, like why water dissolves salt and has a high boiling point. Sometimes one atom donates both electrons in a shared pair. That's a coordinate covalent bond. For example, ammonia, NH3, can donate a lone pair to a hydrogen ion, forming NH4+. Once formed, it behaves like any other covalent bond. Some molecules, like benzene, have resonance, where electrons are delocalized across multiple atoms. That delocalization adds stability and affects reactivity. Now, ionic bonds. These form when electrons are transferred, not shared. Sodium, Na, has one valence electron. Chlorine, Cl, needs one. Sodium gives its electron to chlorine. Sodium becomes Na+, chlorine becomes Cl-. Opposite charges attract, forming an ionic bond. But it's not just one NaCl pair. In solid salt, ions form a crystal lattice, a repeating pattern of positive and negative ions. That lattice explains salt's high melting point and brittleness. The energy released when the lattice forms is called lattice energy. Ionic bonding is favored when the energy gained from forming the lattice outweighs the energy cost of transferring electrons. Next, metallic bonding. In metals, atoms lose their valence electrons, forming positive ions. But the electrons don't go to specific atoms, they're free to move in a sea of electrons. This explains why metals conduct electricity. The electrons flow. It also explains why metals are malleable and ductile. The ions can slide past each other while the electron sea holds them together. And it explains why metals are shiny. Electrons interact with light. Some substances form giant covalent networks. Diamond is a good example. Each carbon atom is bonded to 4 others in a 3D structure. That's why diamond is so hard and has a high melting point. Graphite is different. It has layers of carbon atoms bonded in hexagons with delocalized electrons between layers. That's why graphite is slippery and conducts electricity. Silicon dioxide, or quartz, is another network solid, very hard and high melting. Now, not all attractions are bonds. Intermolecular forces act between molecules and are weaker than bonds, but still important. London dispersion forces are present in all molecules and arise from temporary shifts in electron density. They're stronger in larger, more polarizable molecules. Dipole-dipole interactions occur between polar molecules. And hydrogen bonding is a special case. When hydrogen is bonded to nitrogen, oxygen, or fluorine, it can form strong attractions to lone pairs on nearby molecules. Hydrogen bonding explains water's high boiling point and the structure of DNA. Bonding also affects molecular shape. Electron pairs repel each other, so molecules adopt shapes that minimize repulsion. This is the basis of VESPR theory. For example, methane, CH4, is tetrahedral. Ammonia, NH3, is trigonal pyramidal. Water, H2O, is bent. Shape and bond polarity together determine whether a molecule is polar. Carbon dioxide is linear. Its dipoles cancel, so it's nonpolar. Water is bent. Its dipoles don't cancel, so it's polar. Bonding affects solubility. Polar substances dissolve in polar solvents. Nonpolar substances dissolve in nonpolar solvents. That's why oil and water don't mix. Bonding also affects melting and boiling points. Stronger bonds mean higher melting points. Network solids and ionic compounds have high melting points. Molecules with only dispersion forces melt and boil at lower temperatures. Conductivity depends on bonding too. Ionic compounds conduct electricity when dissolved in water because the ions are free to move. Metals conduct as solids, thanks to the electron sea. Most covalent compounds don't conduct electricity. To go deeper, chemists use 2 main bonding theories. Valence bond theory says bonds form when atomic orbitals overlap. It explains hybridization, like sp3 orbitals in methane. Molecular orbital theory says atomic orbitals combine into molecular orbitals that extend over the whole molecule. It explains things like why O2 is magnetic and how electrons are delocalized in benzene. So to sum up, atoms bond to lower their energy. They do this by sharing, transferring, or delocalizing electrons. The type of bond, covalent, ionic, or metallic, depends on how the electrons are arranged. Bonding determines structure, shape, melting point, solubility, conductivity, and reactivity. It's the invisible glue that holds the universe together.